Welcome to the most successful Starship flight yet. After countless challenges, delays, and setbacks, a true breakthrough has arrived. As Musk praised, it was great work by the SpaceX team. The flight was nearly flawless for both Super Heavy and Starship, showing that the major issues have been overcome. So what exactly happened, and how remarkable was Starship's success on Flight 10? Let's dive into the details in today's episode of Great SpaceX. 3 months since the last flight, and after enduring 2 scrubs, it's safe to say that emotions have run high. The anticipation, the tension, and the hopes of seeing history unfold once again all converged in this moment, and SpaceX did not disappoint. What we have just witnessed was a flight that was executed with an impressive level of precision, one that showed progress at nearly every step. The pre-flight sequence was smooth and well coordinated. Critical steps such as fuel loading, engine chill, and activation of the water deluge system all went as planned. This time, not a single hold command was triggered, which is a major improvement. It strongly suggests that previous issues such as the oxygen leakage in the SQD system has been resolved. Thanks to these refinements, the vehicle was fully prepared and ready for liftoff without delay. And then came the moment we had all been waiting for. Once again, the staggering power of Starship's 33 Raptor engines came alive. With more than 7,000 tons of thrust, the largest rocket in the world roared off the pad, continuing to demonstrate that it is not only powerful but also capable of sustaining controlled flight with unmatched energy. At T plus 1 minute and 33 seconds, however, one engine in the middle ring shut down. This was unfortunate, and it is an area that SpaceX will need to address to secure maximum thrust reliability in future flights. Even so, the loss of that engine had little impact on the vehicle's trajectory. Starship pressed forward, both stages successfully clearing the most demanding phase of flight as they moved toward separation. At T plus 2 minutes and 50 seconds, the separation process began. Outer and middle ring engines shut down, and thanks to the hot staging mechanism that allows the upper stage to ignite while still attached, the transition was remarkably smooth. This is where the journey of each stage truly began. For Super Heavy B16, the improvements to the hot staging process enabled it to carry out an active flip maneuver, assisted by the thrust of the ship. This maneuver is designed to optimize fuel use and pave the way for future efficiency. The boost back burn followed, though the previously damaged engine failed to reignite. After stabilizing, the booster shut down its middle ring engine, leaving just 3 operational engines to guide its return. By T plus 4 minutes and 45 seconds, the hot staging ring was successfully jettisoned, and the booster descended into the transonic regime, this time at a higher angle of attack compared to Flight 9. As it approached its target splashdown zone, the landing burn sequence engaged. 13 engines roared to life, but the damaged engine once again failed to ignite, marking a full loss of functionality. As deceleration completed, the middle ring engines shut down, except for one. Interestingly, this lone middle ring engine was kept active deliberately to balance thrust against the 2 functioning inner ring engines. This configuration allowed the booster to attempt a new kind of test, proving a potential backup landing solution for future missions. Ultimately, B-16 reached the ocean. SpaceX's onboard cameras cut out before impact, but external sources later confirmed that it exploded upon contact with the water. While this result may seem dramatic, it is important to remember that the booster was never intended to survive an ocean landing intact. Splashdowns like this serve as controlled tests, and the near-perfect execution leading up to that moment was an undeniable success. Turning to Ship 37, the upper stage that had been under intense scrutiny after a series of previous failures, the story was even more remarkable. Ascent was smooth, with no signs of the issues that plagued earlier missions. Problems such as harmonic vibrations in the engine compartment, fuel leaks, and hardware malfunctions had all been corrected. At T plus 17 minutes, attention shifted to the payload bay. This was a critical moment because Starship had yet to successfully deploy payloads in orbit. The bay doors opened without issue, a major milestone considering past failures with the door mechanism and nose cone leaks. Just 2 minutes later, the payload dispenser moved into position, and at T plus 19 minutes and 11 seconds, history was made. For the first time, Starship deployed payloads into orbit. Over the next 6 minutes, all 8 simulated Starlink satellites were released one by one, with flawless precision. The payload system operated so smoothly that it seemed SpaceX had already mastered it long ago. This moment marked the beginning of Starship's true contribution to orbital infrastructure. The mission then transitioned to its next objective, in-space engine relight. At T plus 34 minutes and 7 seconds, the flight's internal cameras switched back on, revealing preparations for this critical test. At T plus 37 minutes and 51 seconds, 3 sea-level Raptors extended into position. Just 4 seconds later, one engine ignited and burned for 3 seconds before shutting down. The test was a success, confirming SpaceX's growing ability to restart engines in orbit. This capability is essential for future refueling operations and deep space missions. Roughly 40 minutes after launch, Ship 37 began its return. Concern quickly arose when observers noticed damage to the lower portion of the aft flap, which had started peeling away. Re-entry subjected the flap to extreme stress for more than 20 minutes, but thanks to design upgrades, the damage remained localized and did not compromise the overall integrity of the vehicle. Another striking detail was the sight of burning debris and ash from the engine compartment as re-entry heating intensified. Every passing minute built anticipation. Despite the visible stress, Ship 37 held together admirably. The heat shield upgrades were performing exceptionally well, and as the ocean came into view below the clouds, confidence surged. At T plus 1 hour, 6 minutes, and 20 seconds, Ship 37 executed its flip maneuver with assistance from its flaps, followed by the ignition of 3 sea-level engines to slow its descent. The vehicle returned to a vertical position, descended through the atmosphere, and touched the ocean's surface. Moments later, it toppled and exploded, just as B-16 had. This was expected, and it echoed the outcome of Flight 6 when Starship's upper stage first managed a controlled splashdown. Despite the fiery end, the mission was an overwhelming success. The ascent, payload deployment, orbital engine test, and controlled descent all demonstrated major progress. Aside from minor issues, such as the one failed booster engine and the damaged aft flap, everything worked as intended. After 3 months of waiting, the results spoke for themselves. Starship proved it could deliver payloads, relight engines in space, and survive re-entry with improved reliability. This was a turning point for the program, showing that the long string of difficulties had been overcome. Success defines this flight, not just a test, but a proof of capability, validation of years of work, and a milestone for human spaceflight. As Musk said, it was great work by the SpaceX team. So, let's join in and celebrate this achievement together. And you can do so by sharing 2 words in the comments, great work. Naturally, such success brought a wave of congratulations from across the aerospace community and beyond. The most notable message came from none other than NASA's top leader at the time, acting administrator Sean Duffy. He shared a statement that perfectly captured the significance of the achievement. Congratulations to SpaceX on its Starship test. Flight 10's success paves the way for the Starship human landing system that'll bring American astronauts back to the moon on Artemis 3. This is a great day for NASA and our commercial space partners. These words carried great weight, celebrating the milestone while linking it to the future of American space exploration. Artemis 3 will rely on Starship to return astronauts to the lunar surface for the first time in over 50 years, and each successful test brings that goal closer. Duffy's statement also echoed the confidence he and SpaceX President Gwynne Shotwell have expressed in Starship's readiness for this historic mission. It wasn't just NASA that shared its enthusiasm. Another voice that stood out was Jared Isaacman, billionaire entrepreneur, pilot, and a close friend of SpaceX. Isaacman, who is leading the Polaris program, offered his own perspective. "Well, that was damn energizing to watch. Congrats, SpaceX team, on an important test flight, real progress toward an interplanetary capability the world eagerly awaits." Isaacman's words underscore Starship's true significance. It's not just a moon rocket, but the foundation of SpaceX's interplanetary transport system, key to reaching Mars and beyond. For someone deeply involved in private spaceflight, Flight 10's success is more than exciting. It's a preview of the future many hope to see. With Flight 10 complete, attention turns to what's next. Hardware for future missions is already in place, and Flight 11 could follow soon, perhaps as early as September. Speculation is also growing that SpaceX may attempt even bolder goals, including the long-awaited two-stage catch. And yet, while Starship draws headlines, the wider space industry continues its own remarkable pace. Rocket Lab, in particular, remains a rising force. On August 23rd at 6:42 p.m. Eastern, Rocket Lab successfully launched its Electron rocket from New Zealand, carrying 5 satellites into a sun-synchronous orbit. The mission was playfully named Live, Laugh, Launch, a title that reflects Rocket Lab's creativity and inspiration in branding its flights. Interestingly, not much is known about the customer behind this mission, as both the owner and payload remain confidential. What we do know is that this flight was the second of 2 missions Rocket Lab had signed with this undisclosed client. The secrecy added an element of mystery, and Rocket Lab ended its live broadcast about 10 minutes after launch, withholding the rest of the mission details. Even with limited information, the mission carried great significance. It marked Rocket Lab's 70th launch of the Electron rocket, a major milestone that places Electron among the most active rockets currently in service. In fact, aside from SpaceX's Falcon 9, there are very few operational rockets with a record this impressive. Electron has become a reliable choice for launching small satellites into orbit, and with every successful mission, Rocket Lab further cements its reputation as a trusted provider. Rocket Lab's growth has been extraordinary. In just 8 years, especially the past 2 to 3, the company has accelerated at record pace. Its August 23rd launch marked the 12th of 2025, putting it on track to surpass last year's record of 14. With 4 months still ahead, that milestone is almost certain. Even more notable, every mission this year has succeeded, proving consistency and reliability. Still, challenges remain. Launch gaps in January and July show the need for a steadier cadence to reach that next level. Looking forward, Rocket Lab is preparing for its biggest step yet, the debut of Neutron. This larger, reusable rocket is designed to compete directly with Falcon 9, challenge New Glenn and Vulcan, and even rival Starship. Its first flight, still targeted for later this year, could redefine the company's future. As SpaceX celebrates Starship Flight 10, Rocket Lab's momentum is equally significant. Together, these companies are reshaping access to space, setting records, and pushing the boundaries of what's possible. The months ahead promise even greater milestones.
There we go.
Yes, this was one of Flight 10's greatest achievements and a key milestone for Starship. For the first time, test payloads were successfully deployed, opening the door to countless futures where Starship supports and builds systems in orbit. And this is only the beginning. How did SpaceX achieve this breakthrough, and what comes next? Let's explore in today's episode of Great SpaceX. You may recall that just 3 months ago, during Starship's Flight 9, we came incredibly close to witnessing history as SpaceX attempted to deploy payloads from Starship for the very first time. That moment, however, never came to fruition. Instead, the ship encountered significant technical problems and caused it to lose control, forcing SpaceX to skip the deployment objective altogether. Now, only 3 months later, that long-awaited milestone has finally been achieved. At 17 minutes after liftoff on Flight 10, the payload door opened successfully, signaling a very encouraging step forward. Rather than rushing the process, SpaceX allowed Starship an additional 2 minutes to stabilize and reach the proper altitude before continuing. Then, at the 19-minute mark, the payload dispenser was raised. On board were 8 simulated Starlink satellites designed to replicate the shape and mass of real payloads. The lowest payload lined up perfectly with the opening of the payload door, and once ready, the drive system gently pushed it out into space. The motion was slow, steady, and precise. Even though these were only test payloads, the sequence revealed an impressive level of mastery. For the first time, SpaceX successfully demonstrated the payload deployment model it has been developing for years. After the first release, the dispenser gradually lowered, aligning the next satellites with the payload door. One after another, each simulated Starlink was deployed in turn. Finally, at around the 25-minute mark, the 8th and last payload exited Starship, completing the process and marking an absolutely perfect success. It's important to note that these payloads were only dummies, released at an altitude of about 190 to 192 kilometers. They will eventually re-enter Earth's atmosphere and burn up, with any fragments falling harmlessly into the ocean. Still, this does not diminish the importance of what SpaceX achieved. The mission was a critical demonstration that Starship's payload deployment system is functional and reliable, paving the way for future flights that will carry real satellites into orbit. To appreciate the significance of this progress, it helps to look back at what went wrong during Flight 9. At the time, many suspected that the failure came from the payload door itself, but SpaceX's official update told a different story. According to their findings, a COPV inside the payload bay damaged the methane tank structure, which led to fuel leaking into the payload compartment. This unexpected issue caused attitude control problems, which forced SpaceX to skip the payload deployment attempt. They also noted that the higher pressure inside the nose cone created additional stress on the payload door mechanism, making it impossible to complete the sequence. Learning from that experience, SpaceX made key reinforcements to the systems aboard Ship 37. Improvements to the COPV and fuel tank helped prevent potential damage, ensuring that the payload bay remained stable and safe during Flight 10. These changes worked exactly as intended, as no such issues occurred this time. Another highlight from Flight 10 was the flawless performance of the payload deployment support systems. The payload door has long been one of the most debated design elements of Starship. Many questioned whether it could open and close effectively while still protecting the payloads inside. On this flight, those doubts were largely put to rest. The door opened smoothly and operated as expected, proving that the design works in practice. That being said, future upgrades will likely make the system even more robust, possibly integrating the door more seamlessly with the ship's hull to create a completely sealed environment. This will be crucial once real satellites with delicate electronics and sensors are launched inside. The dispenser system also performed admirably. It lifted and lowered the payloads with precision, and the ejection process was gentle yet effective. The entire deployment sequence lasted only about 6 minutes, which is remarkably fast for such a complex mechanism. As SpaceX continues to refine the process, the speed and efficiency of deployments will likely improve even further. One area to watch closely is the transmission system that powers the dispenser. It must be thoroughly checked and reinforced to ensure smooth operation in every scenario, preventing any risk of jamming or misalignment. Altogether, SpaceX has now proven that its unique payload deployment system works. Unlike the Falcon 9 or any other rocket currently flying, Starship's approach is entirely new. Instead of placing payloads on top under a fairing, Starship carries them inside a massive payload bay with a door mechanism, more akin to a cargo aircraft than a conventional rocket. This design opens up entirely new possibilities for how payloads can be transported, deployed, and serviced in space. Flight 10 also gives us a glimpse of Starship's impressive payload capacity. The dummy payloads used on this mission were designed to replicate the upcoming Starlink V3 satellites, which are significantly larger and heavier than the previous versions. The fact that Starship deployed 8 of them with ease demonstrates the scale of what is possible. In future missions, that number will almost certainly increase as SpaceX optimizes the deployment process. With this accomplishment, Starship has crossed another threshold in its development. The path to carrying real payloads, including Starlink satellites, lunar cargo, and eventually crewed missions, is now clearer than ever. The lessons learned from Flight 9 and the triumph of Flight 10 show just how quickly SpaceX is solving problems, upgrading systems, and moving closer to its long-term goals. What began as a cautious demonstration with dummy satellites may one day be remembered as the first step toward Starship's true calling. Deploying massive constellations, constructing orbital infrastructure, and delivering the payloads that will carry humanity further into space. And that is the foundation for SpaceX to confidently move forward after the resounding success of Flight 10. The mission not only proved that the payload deployment system works as intended, but also created the momentum for what comes next in the Starship program. The next step is clear. SpaceX will likely increase the number of payloads on upcoming flights to test the true limits of Starship. Personally, I expect to see more than 33 payloads in a single flight in the near future. The reason is simple. Each Starlink V3 satellite weighs about 1.9 tons. Once Starship demonstrates the ability to deploy more than 33 of them at once, it will surpass the maximum payload capacity of Falcon Heavy, which currently holds the record with 63.8 tons to low Earth orbit. This milestone is essential. It would mark the point when Starship proves that it can replace the Falcon family and fully carry the future of SpaceX's satellite launches. Of course, that is only the beginning. SpaceX's ambition is to push the limits continuously, especially with the arrival of Starship V3. The company's stated goal is to eventually reach more than 200 tons of payload to low Earth orbit. That number is staggering. It means each launch could carry 100 satellites or more. To put that into perspective, a single Starship launch could accomplish what currently requires several Falcon 9 launches. On the way to that goal, SpaceX will gradually conduct missions with real payloads. At first, they may be deployed in smaller numbers to ensure that each step is successful and thoroughly tested. But beyond just counting payloads, the more significant objective is achieving full orbital capability. This step is not only about proving Starship can release satellites into space, it represents a milestone for the entire program, showing that Starship can reach orbit and perform complex operations there. If everything goes well, I hope we might see this as early as Flight 11. Looking at the near future, the success of Flight 10 and the opportunities that Flight 12 will bring, which is expected to be the final version 2 flight, will give SpaceX the confidence to fully transition to V3. This next-generation Starship promises to be improved in nearly every aspect, from propulsion to structural design to payload handling. The first Super Heavy booster of V3, B18, is already nearing production completion and should undergo testing soon. At the same time, the first components of S-39, the first version 3 spacecraft, have already been spotted and are expected to move into full stacking in the coming weeks. All signs point to a V3 debut later this year, and with it, the opportunity to see even more advanced payload deployment demonstrations. SpaceX's next great challenge is orbital refueling, the key to long-distance missions. Though payload deployment and refueling seem different, both demand precision, complex operations, and reliability in space. Flight 10 proved Starship's ability to handle delicate maneuvers and even saw a successful in-space Raptor relight, laying the groundwork for docking and fuel transfer between starships. Looking ahead, payload deployment opens doors to rapid Earth-to-Earth transport and, more critically, lunar and Martian missions where reliability is essential. With this breakthrough, Starship's payload system has advanced from concept to proven capability in a single flight, an achievement that fuels confidence in humanity's path to the stars. Now shifting gears, let us talk about an equally fascinating development from NASA and Google, which are taking a bold step in preparing the challenges of long-duration space exploration. The two organizations are working together to test an artificial intelligence-powered medical assistant designed to support astronauts on missions where communication with Earth may be delayed or limited. The project is called the Crew Medical Officer Digital Assistant, or CMODA, and it functions as a clinical decision support system. Its primary purpose is to give astronauts a tool to self-diagnose and treat unexpected symptoms when quick advice from Earth-based doctors is not possible. This is especially important for future missions to the Moon and Mars, where communication delays could be significant. For Mars missions, for instance, round-trip communication delays can last up to 45 minutes, which makes real-time consultations impossible. On August 8th, a Google representative provided an update on the program, explaining that the AI system has been trained on spaceflight medical literature and uses advanced natural language processing and machine learning techniques. Its goal is to provide safe, real-time analysis of crew health and performance. Early trials have already tested CMODA in a variety of medical scenarios, and the initial results suggest that its diagnostics are reliable based on reported symptoms. NASA and Google continue to refine the system in collaboration with medical professionals. This technology could revolutionize spaceflight. Astronaut health has long been a challenge in microgravity, but tools like this could give humanity greater confidence to push exploration further. Its timeline for readiness is uncertain, though it would be a major asset for Artemis 3 and could even be integrated into Starship for long voyages. The benefits extend to Earth as well, offering vital support in remote or underserved regions where medical care is scarce. If successful, this AI assistant could transform astronaut care in space while improving healthcare for countless people on Earth, advancing both exploration and human progress.
3, 2, 1. We have liftoff.
volts pitching downrange.
Booster chamber pressure nominal.
All right, we're a little over 40 seconds into flight. 33 out of
Booster and
33
ship,
Raptor
avionics,
engines.
power and telemetry nominal.
Getting good call outs, healthy systems on the booster as it starts to pitch over the Gulf. All right, we're a little over 1 minute into flight, about to pass through max Q.
Max Q.
All right, so we are through the period of maximum dynamic pressure, max stress on the vehicle as it continues to fly.
Our next major event is going to be hot staging, which is happening in just over 90 seconds from now. To get ready, the booster will shut down all but 3 of its Raptor engines. The clamps holding the 2 stages together will release, and the Starship second stage ignites its engines. The ship then separates from the Super Heavy booster and heads to space. At the same time, the 3 engines still firing on Super Heavy will flip the booster around. 10 more engines will ignite for the boost back burn, putting the first stage on the path for splashdown in the Gulf. As we mentioned earlier, the hot stage will be jettisoned for this flight, and that should occur just after the boost back burn. So we're about to shut down the first stage and perform hot staging. So let's just watch and listen.
All right, seeing the engine start to throttle down.
MECO. Ship ignition. Boost back burn startup.
Stage separation.
Stage separation confirmed. We've got 6 engines running on ship. Booster is doing its boost back burn, continuing now towards its splashdown site in the Gulf.
Ship
We are
Raptor
seeing
chamber
all 6
pressure is
Raptors
nominal.
lit up on ship. You heard them report ship chamber pressures nominal, so that chamber pressure, just that expected thrust level in those Raptor engines on the ship. 3 vacuum optimized,
Ship
3 sea
avionics,
level,
power and
all
telemetry
looking
nominal.
good. There's a view into the business end from the ship.
Boost back burn shutdown.
All right, so at this point, we finished our boost back burn, so that was shut down. So that's the first of the 2 burns after a launch that the booster is going to do today. So now it's headed towards the Gulf. It's not going to be quite as an aggressive of a flight down. We relaxed that angle of attack a little bit, but we are then going to be looking for it to do its engine tests for the landing burn, and those are going to be a little unique this time.
Yeah, typically we start with all 13 inner engines lit for that landing burn and bring that down to just the center 3. But one of our test objectives for today is to simulate what an engine out situation would look like. So we're going to be intentionally turning off one of those center 3 and instead lighting one of the engines from the middle 10 ring.
Yeah, we did see one of those engines in the middle ring shut down during the initial ascent. Oh, looks like we have hot stage jettison. You can see it floating away there to the left of the booster. Yeah, we did see one of those middle engines shut down during the ascent. Again, we are resilient to engine out on Super
Starship
Heavy.
Flight
That's why we're
nominal
able to get
trajectory.
through our ascent. Starship flying on the expected path. There's still a chance that engine could be back in the mix for the very start of the landing burn, so we'll see if we light up all 13. But we've even done a landing burn at the tower with an engine out, so very resilient. We'll see how it does on its way down to the Gulf, though. All right, so we got a couple of minutes. That landing burn start should be just about 40 seconds away. That's always rad. You can see the boost plume itself in the background as it was coming in. All right, about 20 seconds to landing burn.
Ship Raptor chamber pressure is nominal.
All right, here we go.
Landing burn startup.
Looks like we got 12 of those 13.
Down to 3, including one of the middle ring. Down to 2. Nice little hover. And landing burn shutdown. And into the Gulf, here we come. And the booster has splashed down.
Incredible flight for booster today.
Meanwhile, back in space, about 7 minutes into today's flight, ship continuing its ascent burn. This goes until just about 9 minutes into our flight. That ship engine cutoff is slated for 8 minutes and 57 seconds. We are going to see those 3 RVAC, the Raptor vacuum engines. Those are the bigger circles in that little indicator on the bottom right of your screen. Those will shut down first, and we continue burning for a couple seconds longer on those inner 3 before we hit SECO, or second engine cutoff.
Yeah, these views are looking great. Once again, thanks to Starlink for getting us these views. It's just incredible. And we just heard the sound from booster.
It's like we just got a late boom from the booster.
Yeah, we have ship engine cutoff coming up here just shortly. And as we mentioned, today's flight test is not an orbital flight, but rather one that demonstrates Starship's orbital capability.
Starship and terminal guidance.
All right, entering the final phase of this burn. Under 30 seconds to go. All right, shut down the vacuum engines.
Ship engine cutoff.
We shut down those center 3. Successful ship engine cutoff.
SECO, baby. There we go. That's what we want.
Nominal orbit insertion.
All right, we just heard the call out for nominal orbital insertion.
All right, so ship is in space. There we go. We're seeing the flaps starting to move into a stowed position. That's why it looks like your camera's moving.
Yeah, exciting to see Starship safely in space, and super pumped to see all the team's hard work in action here today. And of course, as guaranteed, it's been an exciting day so far. We successfully lifted off right on time at 6:30 p.m. Central Time. Thankfully, our weather was looking good today. Yeah, and booster, we had our soft splashdown in the Gulf, so ship continues on.
Yeah, ship able to complete its ascent burn all the way in. You can see some of the shadows start to creep as it's going to be eventually flying into an orbital nighttime, so we'll see some daylight start to go away. But ship is in orbit, completed its burn, and I mean, that's just the beginning. Now we've got a whole bunch more to go. So we've got some exciting demonstrations
Ship
planned
FTS is
while
safe.
we're on orbit. So that right there, we just saved the FTS, the flight termination system. That's that automatic flight safety system we have on the vehicle. So that is now turned off while ship starts its coast period. We are coming up, our next milestone is going to be the deployment of those Starlink simulators. We've got some payload inside of Starship that we're hoping to deploy into space for the very first time. That deploy is supposed to start at about 18 minutes and 27 seconds into the flight, so just about 7 minutes from now. That deploy will take place over a couple of minutes. It'll go about one satellite a minute, so we'll be spread out over that. It might get a little dark, but we've got a couple of views that we can show you to see that deploy in action. After that, we're also looking to do a relight of a single Raptor engine while we are in space. We've done this once before. This is not necessary to deorbit, as we are in a suborbital trajectory, but this is essentially a chance to test out what we need to be able to do a deorbit burn. So we'll be doing that a little bit later in the flight, about 37 minutes or so into the flight, and then we get into reentry. We're looking to get that light show and, more importantly, get that really critical data about the ship's heat shield.
Yeah, exactly. At about T plus 45 minutes, we'll be heading for reentry. Again, running those experiments with the tiles. We're going to be doing missing tiles, metallic tiles, and also intentionally loading those vehicles' flaps. Hopefully, we'll also see a splashdown in the Indian Ocean today.
Yeah, we were able to get to a reentry last time, but we didn't have full attitude control, so we weren't able to go in, heat shield first the way we're designed to. So we ended up losing contact with the ship before we could make it all the way through. So you still get data, but you're not really getting the data that we want to make sure we're kind of stress testing the vehicle. As Amanda just said, we removed a bunch of tiles, and we do this in some intentionally scary places on the vehicle because we're really looking, are there spots that were vulnerable to this? Before we ever start moving towards, putting ship into a full orbital mission to then do reentries a little bit later on. So really, really critical to get that data, really looking forward to a controlled reentry.
Yeah, for sure. As we always say, our main payload is data, but today we also have some actual payload on board, and those simulators that Starship will be deploying, we'll see coming up here in just a few minutes. These are dummy satellites that are about the same size as our V3 Starlinks. We have 8 in the Starship PEZ dispenser and expect to deploy at a rate of about 1 per minute, as Dan mentioned earlier. Starlink is critical in all of our flights on Starship to get our main payload data, as we always say. And in fact, it's Starlink that's currently providing these views you see as Starship cruises a couple hundred kilometers above our home planet and provides real-time telemetry through every phase of flight.
Yeah, we took a peek inside of the Starship payload bay there for a second. So there's 8 of them there. They kind of look just big steel plates, essentially. They're roughly the same size as those V3 satellites. When we do get that view inside of the payload bay, the payload door will kind of be on your right, and we'll start to see them go out like a PEZ dispenser. Yeah, here's a look inside. So those right down there in the center, they're kind of 2 stacks of 4 on either side, and then the payload door is just to their right. And so we'll look to see that open, and then those satellites start to go. We vent the nose cone, so we essentially bring it down to vacuum before we open the door. That was one of the things we ran into on the last flight, as when we had that fuel diffuser fail, the pressure in the nose cone became basically too high for the actuator of the door to open. So that's why we weren't able to get the door open that time. We have not seen anything like that on this flight. Everything's looking good with our fuel tank and our fuel press system. So we are hopefully just a couple of minutes away from seeing that payload door open. and getting to our first ever payload. It's not the first payload we've ever carried, but it's the first one we're going to try and shoot off into space. All right, so I think we're supposed to open the payload door in just about a minute and change. And you're seeing a little bit of residual gas. And we opened the door once. I want to say it was back on Flight 3 when we were able to make it up into space. And you'll kind of see a lot of that gas rushing out into the vacuum of space. It's the residual that's left over after we've already vented it down. So kind of a cool light show. And then we'll get ready to deploy those payloads out. And as we mentioned, so we have crossed over now at this point into an orbital nighttime. So views from the outside will get pretty dark, but we'll see what we can see. We do this by design. We've been launching these later in the day here in Texas to try and get daytime views when we splash down. So it's daytime over in the Indian Ocean, where we are currently headed.
Just a few seconds until we expect those payload doors to open.
All right, one more time. Open the pod bay doors, Hal. So we are currently in payload deploy prep. And the door is open. All right, so the payload door is open. We should see the first satellites start to deploy at about T plus 18 minutes and 27 seconds. So should be only about 30 seconds. So one step closer. Hal listened this time. He cooperated. He opened the payload door for us. There's a view kind of behind the Pez here looking out into the vacuum of space.
About 15 seconds until payload deploy.
Ship has transitioned to payload deploy. There we go. Pew pew. Been waiting way too long to do that. There we go.
There goes another one. Super super exciting moment, as you can hear the energy in both Hawthorne and Starbase. Everyone's super excited for finally getting to deploy some of those simulated satellites.
Pez system moving down. Next row. There we go. As we said, we're going to do about one every minute or so. And this is just kind of a dress rehearsal for when we're going to be deploying the V3 satellites. And these are just a massive, massive increase to Starlink's capability. Each one of them has it's 60 terabits per second of capacity that's going to get added to the network per launch. That's 20 times more than what we're adding with every single Falcon 9 launch today, which, you know, step increase in capability. There goes another one. All right, so as we said, we've got 8 total that we're going to go through today. It's about a minute for each one, but looking good on payload deploy. All right, so we're about halfway through. When we actually start launching the V3 Starlinks on Starship, we're going to be flying about 60 each time. So it'll be about an hour to get through a full stack. But again, it's just going to be a massive increase in the amount of bandwidth. It's going to enable, you know, gigabit upload download for people with Starlink, you know, anywhere on the planet. And for us, Starlink is just a tremendous part of just the Starship flight test program.
Yeah, absolutely. Always getting us that data, and yeah, the amazing views we have on the vehicle today.
Yeah, views brought to you by Starlink of us deploying Starlink simulators before we deploy actual Starlinks. How deep does it go? All right, another one firing out. Pez looking smooth today. All right, looks like we've got one left.
Almost there.
Yeah, there you go. One remaining, so 7 of the 8 have been deployed. One more to go. And then we will have completed our first ever payload deploy operation. Just a reminder, we're on a suborbital trajectory. These satellites on that exact same suborbital trajectory, they're going to burn up entirely and are on that same trajectory towards the Indian Ocean. So the last one has been deployed. Starlink simulator payload complete. Heck yeah, everybody.
Loving the energy from Starbase and Hawthorne.
We are expecting the relight of a single Raptor engine. That should be coming up in just a little under a minute. We're going to be lighting just one of those Raptor sea levels in the middle there. This is not a deorbit burn. It's a demonstration of what we'll have to do for deorbit burns. But we've done this once before. This is something we're really going to have to do when we're doing orbital missions. So it's a pretty critical test. We are just a couple seconds away. Sorry, we're about 20 seconds away, psych. So we got a little bit more time. So we are going to see one of those Raptor engines light back up. We are through the deorbit demo gate, so we should be seeing it momentarily.
Relight demo startup. And shutdown.
All right, looks like we confirmed the relight of one of those center Raptor engines. Second time we've done that. Super exciting.
Nominal
Huge
orbit
congrats
insertion.
to the team on this milestone. Very exciting to see.
That was a cool light show. Yeah, I get to do a mini version here. So again, that's going to be really critical for when we're doing deorbit burns. Like as you're going through, which if you don't have one of these, my God, they're so much fun. But like you're able to actually like light. Oh, Dan, turn it on. Light that engine. Not set my co-host on fire. And that's what we'll eventually do to, break out of orbit, come back down to Earth. So really cool to see one of those engines light back up again in space. That was our last in-space thing.
Very exciting. We're going to be heading back for re-entry at about T plus 45 minutes. So we're going to take another quick break, and we will see you soon.
All right, so we are back. We are about 45 minutes into the 10th flight test of Starship. And as you can see, the light show has started. Re-entry has begun. We are starting to re-enter the Earth's atmosphere. We're moving about 5 times the speed of sound, and we're about to start barreling through the Earth's atmosphere and head for a splashdown in the Indian Ocean. We don't plan to recover the spacecraft today, but if we do make it all the way down to the water, who knows? But the goal of this part of the flight is to learn as much as we can about the ship's heat shield. A fully reusable, rapidly reusable heat shield for a spacecraft has never been done before. It's one of kind of the hardest engineering challenges still out there for us. And so this is a time to really dig in and get that data.
Yeah, absolutely. And re-entry is a critical phase of flight, so we'll need information on how the ship's system end up performing. And Starlink will also help us gather as much data as possible, which is really the main reason why we do these flight tests. Starlink provides us with one more path to collect data to help us rapidly iterate on Starship's design. And if the ship manages to make it all the way to re-entry, we'll collect valuable data on the spacecraft flying through the Earth's atmosphere at hypersonic speeds or more than 5 times the speed of sound.
Yeah, throughout history, a lot of times this is when you go into just a complete data and insight blackout, where that plasma sheath builds up around the outside of the spacecraft that blocks all of your signals that are trying to fight through to talk to either satellites out in space or towers down on the ground. Starship's big size kind of gives us awake, but what really helps us punch through is the fact that we're using Starlink. We're operating at just a much higher frequency. That's not what we want to see. So we just saw some of the aft skirt just take a hit. So we've got some visible damage on the aft skirt. We're continue to re-enter though. And again, we are intentionally stressing the ship as we go through this. So it is not guaranteed to be a smooth ride down to the Indian Ocean. We've removed a bunch of tiles in kind of critical places across the vehicle. So seeing stuff like that is still valuable to us. We are trying to kind of push this vehicle to the limits to learn what its limits are as we design our next version of Starship. So 47 minutes, 45 seconds into the flight, excitement ticking up a little bit on reentry already, but the light show is continuing. This reentry is going to take about 20 minutes or so until our planned splashdown. We were trying to splash down about 1 hour and 6 minutes into the flight.
Yeah, and one day Starship is designed to land on Mars where there are obviously no runways or other humans to help us out. So we are doing propulsive landing instead of more traditional means such as parachutes. And propulsive landing enables us to have more rapid reusability with these vehicles.
Yeah, the ship itself, it's a little over 50 meters tall. We've got those 6 engines on board, the 3 vacuum, the 3 sea level, and they're down in that aft skirt region, which
flaps have control.
All right, so at this point, the flaps have control. That means we're getting into a dense enough part of the atmosphere that the flaps can start controlling us. We're not only reliant on those kind of reaction control system thrusters.
We're going to continue hearing some callouts as the ship makes its way back to Earth. So when we hear entry max heating and entry max Q, that will mean the ship has made it through the maximum heating and aerodynamic loads it will experience as it returns. So if it makes it through those, we can say we're doing pretty well.
I will say I'm happy re-entry cleaned off this camera for us. It was a little dirty from the weather, so thank you, Plasma, for giving us this view as we start coming down. The hit we saw to the skirt, definitely interesting. I will note, when we started doing these missing tile tests, we were intentionally removing them only in the skirt, as that's, you know, that's not over your fuel tanks or anything else that's kind of structurally critical for keeping the entire vehicle together. That obviously exposes your engines, so that could do some things for our landing burn, but for now, we are obviously continuing with this reentry. We are committed. Indian Ocean, here we come. 50 minutes since launch. We're going to see those colors start to build up a little bit. We are at the point where we're in dense enough atmosphere that the flaps have control. So about 74 kilometers in altitude. And you were starting to see some sunlight, so we intentionally time these launches right now so we have daylight. The sun should actually come up over the horizon on Starship in about 3 minutes. So as we get a little bit further into this reentry, that inky black below you is going to start to look like clouds and hopefully a bright blue ocean as we make our way down onto the other side of the planet. We've got these cameras. These cameras are really cool. We added these several flights ago, looking directly at the flaps as not just the heat shield, but these flaps, how they're able to control the vehicle, withstand that reentry, the seal locations, so kind of where they connect to the ship itself are some of the most critical. We will do missing tiles on those where, again, we're trying to... We're kind of being mean to this Starship a little bit. We're really trying to put it through the paces and kind of poke on what some of its weak points are. I mean, we even have missing tiles over some of those fuel tank sections of the ship itself. And so we're really trying to see what are our limits. We're doing this over a completely empty area over the Earth. Look at our Raptors there. We are... Assuming we make it all the way down to the ocean in one piece, we will attempt a flip and a landing burn. We do have at least one buoy, everybody's favorite camera person, out in the Indian Ocean right now, being powered by Starlink. So that's at our planned landing location. So if we're able to get any live views of the ship, that'll essentially tell you that we nailed our target. Able to do that on our 6th flight test, do it in the daytime, which was really exciting. All right, so we're about 10 minutes until we're probably going to start hearing some of the other big milestones coming up.
Yep, in about 10 minutes, like Dan said, Starship will be transonic. This is going to be the period of flight where the velocities of airflow surrounding and flowing past the vehicle are concurrently below, at, and above the speed of sound, so somewhere in the range of Mach 0.8 to 1.2. For reference, commercial jets have a range of cruising speeds, but most of them fly at speeds between Mach 0.74 and Mach 0.85, so that's 480 to 575 miles per hour or 770 to 930 kilometers per hour.
Yeah, and after transonic comes subsonic. That just means you're slower than the speed of sound. We're still well in excess of that right now. But by the time we hit subsonic, we're essentially belly flopping down. There we go. There's that sunlight. So we're seeing the Earth now come back into view. One of the other things we're doing during this, and you're going to see Starship kind of pitch in some pretty, not extreme ways, but a little extreme, as we're trying to really stress the structure of the ship itself, specifically those aft flaps. So the ones in the very bottom of the vehicle. We're pushing not just how well does the heat shield hold up, but how well does the ship structure hold up. We are pushing it beyond essentially what we think we'll have to fly at to do something like a return to launch site. So again, may not be a very smooth ride downhill, but we're doing that by design. We're really trying to find what are the edges that we can operate at, build up a good data set. But sun is up, clouds and water down below us. We are just about 10 minutes away, a little less than 10 minutes now, until we start hitting transonic and then subsonic. Once we hit subsonic, we're basically just belly flopping. All right, so about 55 and a half minutes in, you can see the sun is up. Again, we intentionally designed these flights to lift off in the evening here so we get these daylight views so we can get as good a video as possible on the ship, assuming we make it all the way down. We've got at least one buoy powered by Starlink that's out there in the landing zone in the Indian Ocean, hopefully giving us a view again. If you see any live views, not from the ship itself, that means we nailed our landing target.
Starship is past peak heating.
All right, we just heard the call out that we're past peak heating, so things are looking good so far.
Yeah, looking good. And at this point, again, the flaps are controlling. So this movement you're seeing is that forward flap moving to try and just maintain control, maintain attitude of the vehicle as we're coming down. Checking in on one of our flaps. We got one of these cameras on all four of the flaps, two in the front, two in the back, giving us really good close-up views. As we obviously don't have a camera that can see the entire heat shield. These give us kind of the best that we can do. But looking at those flaps is those are just, super critical for controlling the ship. You have some ability to maneuver kind of cross range. So as you're coming in, you can see in that indicator at the very bottom right that we've pitched up quite a bit. So again, we are maximally stressing those aft flaps right now. Looks like we got a little bit of burn through the very bottom part of it. Everything's still looking good. Ship maintaining control. We should be just about 5 minutes away until we hear that we're transonic. Still a little bit toasty on the aft skirt of the vehicle as we continue coming in.
Again, we are intentionally stressing the flaps so we can learn all we can.
All right, so now we're already well past peak heating. Just about 48, 49, counting down to 48 kilometers in altitude. Expecting that transonic to come, so transitioning between the speed of sound and subsonic slower than the speed of sound in just a little under 4 minutes from now. And right now we've got kind of a lot of forward momentum, a lot of forward velocity, and then eventually by the time we hit subsonic. All right, here we go. So this is what we've been talking about, where we are going to essentially try to fully deploy those aft flaps and really stress them out. So again, this is meant to test the extremes for the vehicle. All right. See those flaps swinging out? Again, we're putting ship through the ringer on this flight in. It's like we're still maintaining control. All right, flaps earning their paycheck today, getting through kind of that max stressing.
Definitely things looking good so far. We're about 2 minutes out now from Starship becoming transonic.
One cool thing to note as we get some of those views showing kind of the whole length of the ship, one of the changes we made after Flight 6 was to change the tile line a little bit. So we had kind of scaled back the number of tiles significantly, as when we go to catch these ships, you don't want to, I think as Elon said, you don't want to shuck the ship as you catch it and knock all those tiles off. So we knew we were going to have to kind of peel back that layer a little bit. And the first time we did it was on Flight 6, and we saw kind of wrinkling and dimples almost in the ship as we were creating these hot spots in the uneven parts of the heat shield. And so to kind of address that, we smoothed it out. That's why you've got kind of that nice smoothed out black line now on the ship. And just looking at it, we can see kind of a little bit of hot spot, a little bit of warping almost. Near the payload door, you can see a little bit of colored patina up above it, but we don't see those kind of deep, almost, they almost look like gouges on that. So it looks like that's been pretty successful. So, all right, we are less than a minute away from hitting transonic. Again, pretty soon our forward velocity is going to look like it's kind of falling off a cliff, and Starship will look like it's falling off a cliff as we essentially go into our belly flop. If you watched some of the high altitude tests or suborbital campaigns, we were able to test that. It was a pretty fundamental, like, can this thing actually fly? And we were able to prove that out with that suborbital campaign. And that's what we're about to see shortly here. All right, so at this point, we've dropped below the speed of sound, so Starship itself is subsonic. We are starting to chill the engines for a landing burn attempt. Landing flip supposed to start in a little over 2 minutes. Subsonic Indian Ocean, we're on our way.
Starship is subsonic.
There we go. Farewell, space. All right, so coming up in just a little under 2 minutes, so we're going to do the flip and the burn. So we're only using those 3 center Raptor engines, the sea levels, the ones that can kind of gimbal, that can move around and steer. Dipping the nose down a little bit. Got 2 of our engines chilled in, waiting on 1 more. So again, we'll attempt to use 3 burns for that initial flip. We eventually go down to just 2 Raptors for the end of the landing burn.
Just about 1 minute now from that landing flip and landing burn start.
Structurally, we're looking good. Got good pressures in our nose cone for everything. Just about 30 seconds. So again, we're going to look for the flip. So Starship's doing its belly flop right now. We're going to do the flip. Swing out. Let's punch through some clouds first. Here we go.
Starship landing burn startup.
Seeing 3 engines. There's our flip. There's a buoy.
Oh my God.
There's a splashdown.